Curve sketching assignment by Maria Jovicic.
Part 1. So we're given this curve and we're told to state intervals or points where the following conditions are true. So the first condition is when is the function concave up? So if we look at our curve and see when it's concave up means that the tangent lines must be drawn under the curve for it to be true. So if we look at intervals that I wrote, negative 3.5 to around negative 1.5, that's all concave up because the tangent lines are drawn under the curve, and that's not including. And then from 0 to 1.7, also not including, it's concave up because the tangent lines are drawn under the curve. Then we're given that y prime equals 0. So we know y prime equals 0 is when the slope of the tangent is 0, so therefore horizontal, which means that we're either looking for a max or a min to occur. But then we're also given that the second derivative must be smaller than 0, which then tells us in fact that we're looking for a max. So in this case, the max that we see is at x equals negative 4 and x around 2.4. Then we're told to find when the function is increasing. So we simply look from left to right in our graph when the function is increasing. So it's from negative infinity to negative 4, not including. From negative 4 to negative 2.5, it's decreasing. From negative 2.5 to 0, not including, it's increasing. At 0, there's a point of inflection where it changes concavity, and then it continues increasing from 0 to around 2.4, and then decreases from 2.4 to infinity, also not including. Then we're told that this first derivative must be smaller than 0 and the second derivative must be bigger than 0. So we know that that means that there's a decreasing rate of change and it's concave up. So if we look at our graph, it's decreasing and it's concave up at intervals of negative 3.5, so right here, to negative 2.5, so right here. And then at 2.5, the minimum occurs. Then we're told when is the function when is y negative, so when is it under the x-axis, when is y prime positive, so when is there an increasing rate of change, and when is the second derivative negative, so when is it concave down. So if we look at our graph, the intervals that follow that is negative infinity to negative 4, not including, and then from negative 1.5 to 0, also not including, because that's all concave down, under the x-axis, and increasing. So this is the graph that I got for part 2. The first thing I did was I plotted all the points that were given to me, my x, my y-intercept, all the other points, and then I looked at my limits. So my limit as x approaches positive negative infinity is 0. So that means if we look at the points closest to positive infinity, and this one's closest to negative infinity, and we approach it to 0, so we put an arrow approaching 0 and this side approaching 0, we know that there must be a horizontal asymptote at y equals 0. And even though there are 2 points here crossing the x-axis, we know that the horizontal asymptote could still exist. So the next thing is the limit as x approaches negative 4 from the right and x approaching negative 4 from the left. So this is the point closest to negative 4 from the right, and this one's the closest to negative 4 from the left. This one approaches positive infinity, this one approaches negative infinity. Therefore, the one-side limits are not the same, so it must be a vertical asymptote at x equals negative 4. Same thing goes for this next limit as x approaching 4 from the left and x approaching 4 from the right. The one-side limits are not the same, therefore there must be a vertical asymptote at x equals 4. The next thing that we were given is f prime at negative 1, 1, negative 4, and 4 all do not exist. That means that at these x values, the function is not differentiable, so the slope does not exist. Specifically at x equals negative 4 and x equals 4, we know that it does not exist because there's a vertical asymptote since the one-side limits are not the same. As for f prime at negative 1 and 1, they're either at this point we only know it could be a cusp or a jump, since all those conditions will make the first derivative not exist. Also, it can't be a point of inflection because, as we can see, the concavity does not change, and we will prove that in the next step. So then we are given f prime at 0 equals 0. So that means it's a horizontal slope, so a point, specifically a max at x equals 0, and the following intervals of increase and decrease will prove it. So as we can see here, f prime at x is bigger than 0, so that means it's increasing. F prime of x is smaller than 0, which means it's decreasing. So if we look at our graph, it's decreasing from negative infinity to negative 4, decreasing again from negative 4 to negative 1, increasing from negative 1 to 0. From 0 to 1, it's decreasing. From 1 to 4, it's increasing. And then from 4 to infinity, it's increasing. So as we can see here, this must be a max. Then we are also given that the second derivative at negative 4, 4, negative 1, and 1, the same points, it does not exist. So, which makes sense because if the first derivative does not exist at these points, neither does the second derivative. So we know that there's a discontinuity, so vertical asymptote x equals negative 4 and 4. And as for f prime, the second derivative at negative 1 and 1, we assume that it's a cusp because the derivative does not exist, but we still have this values at these points right here. Next, we're given the second derivative must be smaller than 0, which means concave down, and when the second derivative must be bigger than 0, so concave up. So if we look at our graph and we check these intervals and follow them, the graph is going concave down from negative infinity to negative 4, so the tangent lines are drawn above the curve. From negative 4 to negative 2.5, it is concave up. At negative 2.5, it's a point of inflection because the concavity changes. So from negative 2.5 to negative 1 is concave down. For negative 1 to 0, it's concave down again. From 0 to 1, it's concave down. From 1 to 2.5, it's concave down. At 2.5, there's a point of inflection where it changes concavity. From 2.5 to 4, it's concave up. And then from 4 to infinity, it's concave down. As we can see here, that follows all the intervals. And that is my graph.
So this is just a picture close-up, so you could pause and look at it.
Part 3. So I was given the function y equals x squared over x squared plus 1, which when I graphed it, it ended up looking something like this. And what I did to get this graph is I first solved for my intercept. So my x-intercept, I let y equals 0, and I solved for x, which gave me x equals 0. My y-intercept, I let x equals 0, solved for y, and I got y equals 0. So I knew my first point would be right there in the origin at 0, 0. Then I solved for my asymptotes, so I looked at my horizontal asymptote first. So by looking at my equation, you can see the degree in the numerator is the same as the degree in the denominator. Therefore, the ratio of their coefficients that are right in front of the variable are the horizontal asymptote. So in this case, it would just be 1 over 1. Therefore, the horizontal asymptote is just y equals 1. So I made a dotted line to show the horizontal asymptote right there on the graph. And then I checked my vertical asymptote by saying the denominator equal to 0. So I noticed when you set the denominator equal to 0, you can't take the square root of a negative 1, which means that the vertical asymptote is not applicable for this function, so it does not exist. The behavior near the asymptotes was found by looking at the behavior near the horizontal asymptote only, since we don't have a vertical asymptote. So I set x as positive and negative infinity because we know that on the right side of the graph, it's positive infinity, on the left side, it's negative infinity. So for the right side, I set a number that's really high on the positive side, so I just did 100. You could choose any number. And I put that back into my original function, so I did 100 squared over 100 squared plus 1, which gave me approximately 0.9999 repeating. So from the right side, we know that 0.99 is right under the horizontal asymptote. So it's right under, which means that from the right side of the graph, the function is approaching the horizontal asymptote from under. And I did the same thing for the left side, so I subbed in a number that's negative, close to the negative infinity, so I just did negative 100. Sub that back into my original equation, which is negative 100 squared over negative 100 squared plus 1. When you square negative, it becomes positive, so you get the same answer, which again means that from the left side of the graph, the function is approaching the horizontal asymptote from under, because it's 0.99 is under the horizontal asymptote. Then to find my intervals of increase and the concavity, I did this on another page. So the first part, to find your intervals of increase, you need to find your critical points. And those are found by finding your first derivative. So what I did first is I did quotient rule to find my first derivative. And I got 2x over x squared plus 1 all squared. And then I set my first derivative to equal 0, which then I solved for x and I got x is 0. So that was my critical point, x is 0. And I made an interval chart with that point, that critical point. So negative infinity to 0, 0, and then 0 to infinity. I subbed in values in between those intervals into my first derivative to see if my final sign would be negative or positive. Again, if it's negative, it's decreasing, so the rate of change is negative. And if it's increasing, it's positive, so the rate of change is positive. And the absolute min is just 0. So to check my absolute min, I took my second derivative, which I will show here how I got it. But I took my second derivative and I subbed in the critical point, so 0, so x is 0. And I saw that that value would be bigger than 0, so that means that it's in fact a minimum value. And this makes sense because if you look at our intervals, it's decreasing all the way up till 0, and then it increases. So the minimum value is 0, 0. And then to see my concavity, I took my first derivative and took my second derivative, again the same way using the quotient rule and the power function rule. And once I found my second derivative, which is 2 times negative 3x squared plus 1 all over x squared plus 1 to the power of 3, because I factored all this out, then canceled that one of them, and I ended up getting this as my second derivative. I set that again equal to 0 to find my critical point. So I just set the numerator equal to 0 because if you set the denominator equal to 0, x cannot equal the square root of a negative number, so that's again not applicable. So you just make the numerator equal to 0, solve for x to get x equals plus or minus the square root of 1/3, which are your critical points. So you use this to put that back into your interval chart and to see your concavity. So again, it chose values in between those intervals to put them back into my second derivative and see if it's negative or positive. Again, if it's negative, it's concave down. If it's positive, it's concave up. But if you get a 0, that means it's a point of inflection. So that means the concavity changes at that point. So as we could see, if we look back at our function here, it's concave down all the way up till negative square root of 1/3. Concave down, again, as we remember, is the tangent lines are above the function. So that whole part up to here is concave down. Then point of inflection is right here, switches concavity, so it goes concave up from negative square root of 1/3 to square root of 1/3, positive square root of 1/3. And then it goes concave down, point of inflection again, and then it changes back to concave down because the tangent lines are above the function. And that was all for part 3.
So this is a close-up picture for part 3. And this is the other side.